Yeah. Okay. So we are happy to have Vaibhav Kalvakota with us, and the title of his talk is the definition of holography. Over to you, Vaibhav.
Okay, so thank you for giving me the opportunity to talk. So I'll be talking about the definition of holography, which is it's kind of loosely based on this paper I wrote, which is an essay with Aisharma and some upcoming work with it. And it's also loosely based on these notes, which you can see over here, um, which will be periodically updated with some musings on holography, generally around ADS, CFT, or de Sitter. So, um, so what's the point of all of this? So dualities in physics have played a very important role. For instance, you've had the electric-magnetic duality, which Ayush recently talked about. So you have the S duality, you have T duality, and so on and so forth. And one of the most important revolutions in theoretical high-energy physics is that of holography, or the duality between a bulk gravitating region and a non-gravitating quantum field theory, which is usually satisfying conformal invariance, but that's not really always the case. So the general idea is you have something like this. So this is your bulk, and over here is your quantum field theory. And in this picture, the cylinder really just it really just denotes ADS. So this is actually bulk ADS. And the boundary is a conformal field theory. So it's a field theory that satisfies conformal invariance, and it lives on the boundary of anti-de Sitter space, which is a family of negative cosmological constant solutions to the Einstein field equations. So string theory gives us a way to establish such a duality in the case of anti-de Sitter space, where the bulk is the gravitating ADS, and the dual field theory lives on the boundary of ADS. The original description was the duality between type 2b superstring theory and an n equals 4 super Yang-Mills conformal field theory. But after that, a lot of generality has been found, and usually you don't really have to invoke a lot of these often complicated and technical string theory details. And at that, what holography really means is very subjective. For a string theorist, holography is this correspondence between supergravity and a superconformal field theory. But that definition doesn't have to be so technical, nor does it necessarily have to stick to this. So that's the objective of this talk, which is to basically talk about what holography really means. And it's a very subjective definition, but we'll just encapsulate some of the facts that holography seems to have. And we will try to point out the most general definition of holography and some more technical details. And in the first half, we will talk about some of the general aspects of holography, and the example will be ADS. And in the second part of this, we will talk about some more mathematical details of holography. And it must be noted that this particular paragraph was written before I completed the slides. So it's not really two halves, but it's actually, I think, three distinct divisions. And so in the first half, we'll talk about ADS. In the second half, we'll talk about some of the mathematical aspects, and in the third half, we'll talk about how we look at these in the context of de Sitter space, which is a positive cosmological constant solutions to the Einstein field equations. And so yeah, we'll either stick between ADS or DS, but you could probably do all of these in the flat space, for instance, flat space solutions, for instance, but they have certain subtleties which we won't really talk about, but you can see, for instance, flat space holography papers. I think some of the more prominent papers have been written by Serveth. So yeah, you can go ahead and take a look at those. So we'll start by talking about the two parts of ADS CFT. So again, in ADS CFT, you have this picture where this is your ADS and this is your CFT, and hence ADS CFT. And what we usually do is the bulk is the more non-trivial part, and we usually understand more of the conformal field theory. So we'll talk about these two halves. So in bulk anti-de Sitter space-time, so again, ADS is just the positive negative cosmological constant solutions to the Einstein field equations, which are these. Where we're now adding the cosmological constant. And so If you take a positive cosmological constant, you get de Sitter space. If you take negative cosmological constant solutions, you get anti-de Sitter space, and you attribute a length scale in terms of this cosmological constant, and so on and so forth. So in the bulk picture, we have, so the basic starting point is that ADS CFT really corresponds to a state operator duality. So the idea is that you have some bulk quantum field theory states phi, and you have some conformal field theory operators O, and there's a duality between these things. And you can also predict that there are some certain subregions in the bulk that are dual to certain boundary subregions. So in general, what that means is you can do something like this. So let's just remove this. So if you take a Cauchy slice, so this is what, this is what a typical Cauchy slice would look like. So this is just the boundary of the Cauchy slice, and this is the Cauchy slice itself. Now, what you can do is you can say that if I have access to just this part of the boundary, which I'll call R, then there's a particular subregion in the bulk, which is dual to this, which we'll call small r. So the duality then becomes, well, we can reconstruct bulk fields. So we have phi, which are in R, and we have operators in capital R, and there's a duality between these two things. And so that's essentially what the state operator duality tells us. And the more concrete realization of this is that you can reconstruct bulk fields, like I said, in the asymptotic boundary limit. So this follows from the extrapolate dictionary, which is to say that if you take the limit in which the radial direction, in which the radial direction goes up to infinity, which is to say that now you're in the asymptotic boundary limit, your fields, it's to say that loosely your fields become particular operators. And so in this sense, you basically say that, okay, well, if I have access to a particular boundary subregion, I can reconstruct these bulk fields as well. And this really implies that there are only certain bulk fields that can be fully reconstructed given access to a particular boundary subregion. And this bulk subregion is called the entanglement wedge for a boundary subregion R. So this small r is really the entanglement wedge, which is a collection of all the bulk fields that you can reconstruct given access to a boundary subregion. And this first was indicated by the holography entanglement entropy formula, which was given by Ryo and Takayama's famous derivation, which tells you that the entanglement entropy of a particular boundary subregion is the area of some minimal surface over 4G Newton. And this gamma r is really just this surface. So it's really just this surface. And so it tells you that you can always fix a unique minimal RT surface. And in that sense, you have an entanglement wedge. Okay, so now the boundary side of things is you have a better understanding of things in general, which is that you can take the large n limit of the conformal field theory to get a bulk description of type 2 B strings, which is the 1997 Maldacena paper. And more generally, the bulk is emergent from the boundary. And a very useful result is that the bulk dual to the thermofield double state is a two-sided eternal black hole. So, so this was Maldacena's 2002 result, which is that you have a two-sided eternal black hole that's dual to the thermofield double state, and you have two CFT copies. And the reason why this is very interesting is it's actually a very, very direct derivation of the facts that you can actually look at holography in a useful context, in a useful setting. And in fact, it doesn't have to necessarily be the eternal ADS black hole. You could do something very similar if you did what's called this purification of states, and you could do, for instance, coarse graining and stuff like that. And in light of this, it is obvious to ask what other general statements we can make about holography, and if we can look at a much more mathematical side of things. So sometimes it's much more easier to just look at the bulk side of things, which is not usually the case, but it's a particular family of scenarios where you have some understanding about the bulk and you would like to understand the boundary. So that's kind of what's going on in DS right now, which is you're trying to understand what the what the actual statement of holography becomes if you have an understanding of the bulk side of things, which is one of the reasons why we always do perturbative bulk calculations in de Sitter. And note that when I say the bulk side of things, we're really ignorant about the bulk side of things, but we just want to understand how these bulk subregions imply deeper mathematics. So now's your excuse to go to sleep if you want, because I'll be doing a bit of mathematical discussion, but I'll try to keep it as simple as possible. And if you have any questions, just feel free to ask me. So I'll just give a really quick motivation about axiomatic quantum field theory, which is mathematicians were interested in quantum field theory for obvious reasons, and there are a lot of mathematical subtleties with how a lot of physicists talk about quantum field theories. And so mathematicians wanted to axiomatize quantum field theories in a way that would be generally applicable. And the general prescription to making sense of quantum field theories is to define a quantum field theory as a monoidal functor from a geometric, or in a sense, a topological category to an abstract category. So I think the most stringent example, which is also the most famous example, is that you could have topological quantum field theories, which are these functors from the category of n Bortisms to the category of k vector spaces. And a much more prominent example of a topological quantum field theory is Chern-Simons theory, which is very, very famous. And in general, these are referred to as functorial quantum field theories. And a very general class of such quantum field theories is what's called as locally covariant quantum field theories, which are functorial quantum field theories that are functors from the category of d greater than or equal to 2 globally hyperbolic manifolds to the category of suitable C-star algebras. And it satisfies some conditions like causality, isotony, covariance, and so on and so forth, which seems like a drag, but in reality, there's a very nice way of looking at it, which is you could take a Cauchy slice. Let's suppose we're working in Minkowski spacetime, so we're working in the four-dimensional flat space. So this is just a Cauchy slice sigma, and I can take a bounded region U, and to this I can associate an algebra AU. And so when you're working with locally covariant quantum field theories, you're concerned with local nets of observables, which are associated to these boundary subregions. And usual quantum field theories have a peculiar property, which is something that I'm sure is covered in most undergraduate quantum field theory courses, which is that in general quantum field theories, the entanglement entropy, which is computed by the area of this boundary, is divergent. And the reason is, well, at least physically, you have infinite modes of entanglement across this entanglement surface. And so mathematically, this can be much more elaborate in the sense that you could say that there's an ill-defined nature of entanglement entropy for certain types of von Neumann algebras, which are a particular class of algebras, which I'll cover in a moment. And this particular issue of infinite modes of entanglement is caused by type 3 von Neumann algebras. And the subscript 1 over here is a little more particular, which is not really that important, at least for this discussion. But yeah, so ordinary quantum field theory is a type 3 von Neumann algebra. And a von Neumann algebra is an algebra with a particular operator topology, as well as it satisfies what's called as a bicommutance theorem. And without going into details, really any quantum field theory has this notion of a von Neumann algebra associated to boundary subregions, and that's one of the reasons why we can also do the same for ADS, which is a much more larger scale development of this almost an algebraification, as you can say, of ADS CFT. So that's one of the things that we want to talk about, which is you can actually have a mathematical program towards holography. And so yeah, so without going into details, the idea is that there are 3 types of von Neumann algebras, which were given by Gell-Mann-Murray and von Neumann, and it was loosely based on the tracial properties, which are of concern to us. So this is a bonus slide, which
just a moment. I was sorry. Yeah. I just wanted to make it precise that not every quantum field theory can be a type 3 one. Generally, you have a type 3 one when you have a large n elements of some. So I think I guess you mistakenly wrote that it's a type 3 one, or not all of them will be type 3. But yeah.
Well, yeah, I mean, I just meant in the
it's type 3 lambda, like And the oneness of this hyperfinite reduction. I believe you are coming. Yeah, I get it.
Yeah, I mean, in general, if you just took a flat space quantum field theory, then I think you can still have a type 3-1. So because there's the motivation towards
for that there is always a large element to have that. But if you start with, let's say, like if you have some Rindler wedge and there is infinite modes of entanglement, that's type 3.
Yeah. Yeah, I was just being a little more specific towards the ADS-CFT discussion. So just to put things into perspective, but yeah.
I get it.
Okay, good. So this is just a bonus slide, so this isn't really you should just take this with a grain of salt, but at least superficially you should just keep this in mind, which is that a little more precisely, we're considering algebraic quantum field theories as a functor from, like I said, the category of globally hyperbolic manifolds to those of C-star algebras. And the objects are smooth D-manifolds with the orientation. So there's usually quadruplets of data for these algebraic quantum field theories, particularly locally covariant quantum field theories. And the morphisms are just smooth isometric embeddings that preserve these orientations. So basically, there's some data associated to these manifolds, and your morphisms are just embeddings that preserve this this data. And the objects in the algebra are suitable C-star algebras, and the corresponding morphisms in the category of algebras are unit-preserving star homomorphisms. There's, I think, it's kind of an open question to actually talk about these generally, but for now, we'll just keep this in the back of our minds. So in general, all this really means that for every bounded subregion, we're attributing a C-star algebra, or more strongly, a von Neumann algebra. And for general subregions with no boundary structures, no asymptotic boundary structures, this von Neumann algebra is typically type 3-1 with reduction to type 2-1. And if you have an asymptotic boundary structure, then it becomes type 2 infinity. And this was a recent result by Jensen, Speranza, and Sorsi. And a nice example of why this is relevant is that the topology of any slice in the Sitter space is closed. And so because of that, you don't have any boundary structures. And so you'll have type 2-1 von Neumann algebras. But it's really just a retro construction of the CLPW paper. So, okay. So types of von Neumann algebras, what does this mean? So there are three distinct types of von Neumann algebras which have different properties. And a nice way of understanding what the intuition for all of these types is to consider where we can define entanglement entropy. So in quantum mechanics, this was really never an issue, and we happily said let there be entanglement entropy and entanglement entropy all over the place. But for general quantum field theories, this is not the case. You have infinite entanglement, and because of that, you don't really have a good notion of entanglement entropy. So a trace does not exist in local quantum field theories, and that's a kind of a result of there being a type 3 von Neumann algebra. And so again, there are three types of these, and there are subclassifications. So you have, I think, relevant to our discussion, like I just mentioned, there's type 3-1 algebras, and you have type 2-1, type 2 infinity, and so on and so forth. But these subclassifications aren't really something we want to go deep into. So there's type 1 algebras, which have a well-defined trace, and this is just your usual quantum mechanics. There's no problems of infinite entanglement or anything. There's type 2-1, which doesn't really have a completely well-defined trace per se, but in a sense, it's kind of much better than type 3. So quantum field theories are, like I said, type 3 algebras, and type 2 infinity algebras are better. Whereas type 2-1 algebras are even better, and type 1 algebras are the best because you can just define entanglement entropy. And type 3 is kind of the worst of them all, and this is the culprit, and there's no well-defined trace, which of course never really stopped physicists. And the way you would go around this is you could just define a short distance cutoff, which creates a sort of a lattice background, and so because of that, it gives you a well-defined entanglement entropy. And that's also one of the reasons why in the RT formula, you saw something like, you would have something like this, without going into the details, over epsilon, and this is a short distance cutoff. And so basically this latticizing is really, really important because that actually allows you to define an entanglement entropy. Physicists, of course, really never never stop because of this, and they would always go around this. And one of the good reasons why you can do that is because there's something called Tomita-Takasaki modular theory, because of which you can define relative entropy, which is something that Araki formally defined. And so bulk quantum field theories are no exception. And in the RT formula, this was explicitly clear. And the RT formula needs a short distance cutoff to be meaningful because it comes from the usual area law for the entanglement entropy. And for type 3 algebras, we can only define relative entropy from the Tomita-Takasaki theory. And most of the ADS-CFT works on information theoretic aspects of such entropy definitions. And I actually have to add something over here, which is prior to CPW, relied on this construction of relative entropy. And so the reason I said prior to CPW, which is a paper by Chandrasekhar and is because it actually is Aaron Wall's relative entropy formula in terms of in terms of a type 2 infinity algebra, which has to do with something called the cross product construction, which turns a type 3 algebra into a type 2 infinity algebra in the case of ADS-CFT. And so you could work with relative entropy in a very reasonable way, but you could change this, like I said, and turn the type 3-1 algebra, which is what we're doing for ADS-CFT, because these are the only type of Neumann algebras that have what's called as half-sided modular inclusions, which is a particular kind of modular inclusion. I don't really want to talk about it right now, but basically the idea is that type 3 algebras can be quote unquote detected, and you could basically turn that type 3-1 algebra into a type 2 infinity algebra, which is not technically much better, but it indeed is a lot better, because in type 3-1 you couldn't define entropy at all, whereas in type 2 infinity you actually have a trace class, and so because of that you can define entropy reasonably. For type 2-1 you would actually have a much better and a much more formal definition of these things, but type 2 infinity is good as well. And this is due to a theorem in mathematics by Takasaki, which is that if you took the cross product of type 3-1 algebras with its modular group of automorphisms, you get type 2 infinity. And we'll just boil this down. So type 3-1 is the usual large n Lulith-Husserl algebra. This thing, R odd, or the modular group, is the modular group of automorphisms of this algebra. And here is the group of time translations generated by the modular operator. And type 2 infinity is the resulting algebra, which is an extended Lulith-Husserl algebra, but you also include the Hamiltonian. There's a lot of subtleties that arise because of this, but fundamentally, this you could also kind of achieve from a 1/n corrections approach, which would be further complicated for our purposes, and we will just stick with the original CPW results, which is the microcanonical ensemble version of the large N algebra, in contrast to the original Witten paper called Gravity and the Cross Products, where you actually were dealing with the canonical ensemble. So we're not really talking about that. So what happens as a result of this cross-productification? So we no longer have to work solely with relative entropy. We can define entropies of subalgebras with a subtlety, the subtlety being that you don't really have subalgebras, but okay. So the bulk dual to the entropy of these subalgebras becomes generalized entropy. And okay, so a note over here is that I said you don't have in general subalgebras. I think you do have subalgebras, but only in particular cases. So for instance, if you took a one-sided black hole and you took a late time limit, then you could in principle just have subalgebras, and those are actually well defined. But that's not always the case, so that's actually a subtlety, but okay. So the bulk dual of the entropy of these subalgebras becomes a generalized entropy, which gives you your quantum extreme surface prescription. And the reason that is interesting is because you can do a lot of things with it. And this usual generalized entropy monotonicity property was also found, as Aaron Wall found in his relative entropy argument, and it was generalized to Killing Horizons as well. And there's ways of working with free products of algebras, and it's not really relevant for us right now. But the idea is that you don't really have to rely on Euclidean path integral constructions, which are, well, complicated to say the least. And you can now work with the QS prescription, which is a very, very cool thing. So the idea of doing this mathematical discussion was to basically say that we understand a lot about ADS-CFT. So in ADS-CFT, we understood loads of things. So let me just find some space over here. So in ADS, we were able to have a reasonable notion of holography from reconstruction. We had a nice algebraic definition of holography in the sense that you could just find a duality between subalgebras and subalgebras, which is a little sister result, which is that for boundary subregions, there are bulk subregions, and as a result of that, you also have boundary subalgebras, which are dual to bulk subalgebras. Okay, so you have some nice notion of reconstruction. You have the notion of subregions as well. So you had entailment wedges. You knew what the entailment entropy formula meant, and so on and so forth. And I think one of the most important things about ADS-CFT is that you have a nice algebraic formalism to it. And among other things, you also have, in general, ways of working with the entropy of arbitrary surfaces. So there's always a nice meaning towards reconstruction for arbitrary surfaces as well. So in order to give you a nice contrast between the difference between ADS-CFT, which is so well understood because of its convenient time-like boundary and space-like infinity, we'll now talk about de Sitter, which is a positive cosmological family of the field equations. Is there a question? Sorry. Okay. So from the cosmic no-head theorem, almost every class of cosmological models become asymptotically de Sitter. And in the context of quantum gravity, this has many interesting consequences because we can also have a general future description of information. So that is to say that if this is your de Sitter, then at the asymptotic limit, which is close to I plus, you can take Cauchy slices and you can have a nice description of quantum gravity at those slices. So see, for instance, Suvreth et al.'s work on Hilbert space of de Sitter quantum gravity and holography information, which is an amazing result. And okay, so if I can actually give myself the liberty of actually detouring from the slides, I think it's really interesting to note that the construction is almost akin to the Friedel construction. So the Friedel work was basically to say that states become something like C plus or C minus with some factors, so ES and E minus S. And this is taking so radially asymptotic slices. So if I took R goes to infinity, then I could find in principle what the Wheeler-DeWitt states are. So just to give you a quick idea, so in the canonical quantum gravity formalism by Wheeler and DeWitt, you have the Hamiltonian constraints. And what this tells you, is that there's a particular constraint, without going into too much details, that certain Wheeler-DeWitt states obey, which is the Hamiltonian constraint. And among other things, it also tells you that in the asymptotic limit, it kind of decomposes into two branches. And in de Sitter, you only have one dominant branch. Well, actually, you should be having two dominant branches, which is not really something that's relevant to this talk, but I think it's just a really important way of looking at de Sitter space versus de Sitter space. Find out holography from the canonical formalism. So for ADS, you can do this. And so for ADS, the asymptotic limit just gives you some conformal field theory partition function. And it actually makes sense because you know what the field theory is. For de Sitter, which you can also obtain, so you obtain something very similar to this. So it's a function of the metric and the matter fields on those Cauchy slices. The thing is, your field theory is not really clear. And at the same time, in de Sitter, you expect to have a non-unitary conformal field theory. And so because of that, this particular formalism of doing canonical quantum gravity and getting these asymptotic states becomes really confusing. And so these are apparently not really CFT partition functions. And there's some interesting links to a bunch of things. So there's interesting links to TC bar deformations, which also links to Cauchy-Slice holography. There's interesting links towards the CPT theorem. And in general, unitarity is a really interesting, it's a really interesting thing in quantum gravity. So, okay, so that's just a detour, not really very self-contained or anything, but okay. So yeah, we can have a general future description of information. Now, there's some kind of problems in string theory because of vacuous and Maldacena Nunes and so on and so forth, but it's still exciting. And again, like I said, you don't really have to understand a lot of string theory in order to do de Sitter, or in fact, ADS for that matter. But I think the string theory background towards ADS is at least, one of the most important things that modern theoretical hydrogen physics has done, which is seemingly not the case for de Sitter. So de Sitter holography has been a dream for many physicists because it describes our cosmology, because we are in an approximately de Sitter universe. And one of the reasons why de Sitter is also interesting is because you have closed slices, like I said, and so you can have some weird properties of holography because of that. And so you have something called complementarity, which is that if you have a bounded subregion U, and we'll call this U bar, then there's a kind of correlation between U and U bar. But and this works quite well for, say, flat space, for ADS and so on and so forth. But for DS, U bar and U are actually virtually indistinguishable. So because these are actually closed. And so because of that, there's no open, in a sense, Cauchy slices. And so that becomes an issue. So you have this complementary strangeness, which is kind of interesting for de Sitter. And yeah, there's a load of interesting reasons as to why you should do de Sitter. Oops, let me just remove this. And also, I think you can see, for instance, Paul's paper, which I think came a year after ADS-CFT. You can see Strominger's paper. You can see Maldacena's paper, and so on and so forth. And there's a load of papers that you can refer to get some nice motivation for de Sitter. And Strominger had a paper on DS-CFT in 2001, which is one of the most popular de Sitter holography setting. And the boundary dual to both de Sitter space is the conformal null boundary at I plus minus, which seems kind of straightforward, even though it's not a convenient time-like boundary. It's at least something that that you can kind of happily stick with. It's not a space like infinity, sorry, but it's at least something that you can do probably. But the issue is, and in fact there are many issues, but some of them have to do with the fact that it's at an asymptotic conformal boundary, which is not space-like, and because of that, if you flow from the boundary, time actually varies, because basically what you have is something like this. So if you move from the boundary, you're also varying your time parameter, your conformal t parameter. So modular flows become either non-trivial or nonsensical, one of those two things, which you were quite well able to do in ADS-CFT. And then most of the other reasons have to do with the fact that the dual theory is non-unitary, which is very intimately linked to this particular issue. Entanglement entropy therefore becomes complex valued, and it becomes something called pseudo entropy. And instead of working with density matrices, you have to work with transition matrices, which are again either non-trivial. Which are either non-trivial or nonsensical. Perhaps they're just non-trivial, and we just haven't really understood their full worth. And I think the biggest problem was too many people were leaving everything to double Wick rotations, and they were like, just do Wick rotations. They said it'll be fun. They said, which is not really the case. It's not really fun. So yeah, it isn't fun. But perhaps static patch is the better setting for these things, because we know that an algebra of observables is clear in the setting. So at least we have a mathematically, at least well understood idea of static patch de Sitter, which was the paper by CLPW, which came, I think, either before or after the CPW paper. So I think that's, yeah, so the idea is that in static batch de-Sitter, there's also the added benefit that because your conformal field theory is living on the stretch horizon, so because you have something like this, your if you float from this field theory, or if you float from this quote unquote boundary, you're not really flowing along with time, because and so you can actually define space like slices, and you can basically work with it solo. And that seems to be an added benefit, but I don't think there's really a very clear explanation as to how you can understand the microscopic physics of static batch de-Sitter. I think TD bar deformations have been very important, and in the static patch setting, you also have to add in the cosmological constant to every step of the deformation, so it becomes TT bar plus lambda 2, because usually the best setting is DS3. DS3 with the boundary being a two-dimensional boundary. So this stretch horizon becomes a two-dimensional manifold, and so you get a lambda 2 thing. And so, yeah, so static patch seems to be good, but overall, de-Sitter has many subtleties. You can also do something called half de-Sitter holography, which is kind of strange, where you basically take your conformal boundary, you kind of cut it in half, and so you have a time-like boundary, and you basically do holography in that sense, which seemingly ties close to deformations, I suppose, but I don't really know if there's an added benefit of doing a construction like that, or I might just be missing something. So overall, this sort of has many subtleties, due to which we don't really know what the precise right notion of holography is, which brings us back to the original question, which is, what is the most general definition of holography? And again, that's a really very subjective, it's a very subjective question. So you could either have a really very string theoretic definition of holography, or you could have a very operator algebraic definition of holography. But in general, you'd have two possibilities. One is that there's a duality between a gravitating region and a very precisely defined dual field theory that lives on the boundary, and the operator algebras are dual to each other, and you have some corresponding subregions on both the sides. So in a sense, you could say that the bulk Fock space is dual to the boundary Hilbert space, which invokes GNS construction. Or you could have a similar idea, but a slightly different approach, which is something called holographic information, which is different in the sense that it involves violating the split property, which also seems to be violated in this case as well, in a sense, which I'll get to in a second. But in general, it lets you have a duality of operators at the asymptotes. And so the de-Sitter picture is not really clear in either case. Perhaps holographic information is much more clear in de-Sitter, but there are still many things to look out for. So the idea of violating the split property isn't really new. In fact, I think Survit has been very active about this. And what the split property tells you is that you can prepare, in this picture that I've drawn probably 100 times right now, you can prepare this this particular subregion from the boundary, from the complement. And in a sense, there's a distinction between the subregion itself and the exterior of it. And what the holographic information proposal tells you is the information about any part of the interior of this Cauchy slice is available on its boundary. And so because of that, the split property becomes inherently violated. And there's a way to axiomatize the split property. And if you were doing locally covariant quantum field theories, this becomes something called intermediate factoriality, which is something I was really interested in for a while. But again, it's I guess tonally a slightly more general approach to the split property, but again, it's just violated in this case. So yeah, so the idea is that algebraic quantum field theory is somehow telling you something about quantum gravity, which is, well, when you're adding gravity to a quantum field theory, you're getting these weird, interesting subtleties and these interesting results, which kind of complicates the already complex quantum field theory physics. And so And to sum up, I think de Sitter is intrinsically a much more technically strange setting to work with. There's also flat space, and flat space is much more straightforward. Not entirely straightforward, but in a sense, it's a little more convenient again, because for flat space, you could just take an algebra over here and kind of localize it. And so your boundary just becomes I plus and I minus. And so in that sense, you could do some geometric constructions with the Bondi mass and so on and so forth. And in that sense, you can again have some similar-ish notion of holography. So yeah, I think ADS and flat space have so far been the better understood sides of the equation, more so than de Sitter space. And so yeah, so the general definition of holography is probably one of these two things. So yeah, that's all I have to say, and thank you very much for your attention. I hope I kept this short enough. So I'll stop here.
Yeah, very good, sir. Thank you. Actually, this is and I think this is what you meant in the last, that gravity is very special. One of the reasons why you should be studying gravity is because of this, I mean, one of the main things is that gravity localizes information on infinity.
Yeah, and yeah, I think that's it's a very profound thing, because I think that also adds to the idea that quantum gravity is much more subtle and a little more different than we ordinarily expect it. Because quantum field theory, yeah, I think anyone can do it, but the thing is, when you add gravity to the setting, it becomes much more non-trivial.
Yeah, because even if you have let's say an empty de Sitter without gravity, that is just type 3. Now, if you include gravity, there's a lot of things, and since you are mostly interested in DS has this, it reduces to type 2-1 when you bound the observer's energy. So gravity is very different from other theories because it localizes information. And I believe, I think this is more into holography of information rather than pure holography. Yeah, and the second thing was, yes, we have the BMS curve for de Sitter, yes. I think you have this boundary data GN and G0. And I think we do this in this using papers across. Although it's not clear, like, what is exactly, because in ADS you have this time-like boundary and a very unitary CFT. In DS you do not have that. And you do not know. I mean, not talking about static patch, but in a global de Sitter, you do not have this. Yeah, and the issue of de Sitter vacuos, I think, although you didn't mention it much, but I think actually yes, string theory is ill-defined in string theory. Do you agree?
Yeah, I agree. I think, well, I'm not really qualified as an expert to, even remotely talk about these things, but yeah, I think there's a huge debate about vacuous and de Sitter, and in general, is DS even a good thing to work with in this holography setting?
Because nobody has
and
found
there's a lot
of
criticism.
In string theory.
Yeah, and among other things, also it's like there's no one-shot stringy way of saying, well, this is DSCFT, because for ADS-CFT it was really very apparent. You could have a good description, but as far as I know, there's really not much of clarity. Firstly, what's the dual field theory? I just need someone explaining me that, because if you don't have a dual field theory, it's not really holography. It's just some.
Or you see, what is your boundary and how is your information being localized? And yes, on the issue of string theory in DS, it's a very subtle issue, of course. And I believe there is a paper recently. I cannot remember the authors, but they claim to have this vacua using KK-LT mechanism. Yeah. Although, I mean, of course, it will take more years to find a vacua like of DS in string theory. Yeah, but cosmologically, it is very important to study DSCFT. Yeah, at least. And, of course, many profound examples of holography, of algebras are coming in. So That is good stuff as well for DS, especially this paper, CLPW.
Yeah, I think it's also worth mentioning that there's a lot of scope in JT gravity and random matrix theories, because we've had Collier's paper with Beatrix Muhleman and wait, I actually don't remember the authors, but yeah, basically that's the thing, because a lot of what we understand in ADS also appealed to JT gravity, and I think that's
People
the thing,
are
because
studying JT gravity in ADS and DS both actually. So, and actually, yes, as we have, I think we agree on this that most of the techniques you can use in ADS cannot be applied in DS. But JT gravity in ADS and DS are being